This session of Scanner School is sponsored by our new training course, An Introduction to SDR, or Software Defined Radios. Now, this course is designed to walk you through the process of not only purchasing, but also installing an SDR, getting the accessories hooked up, and getting the software installed in your computer so you are ready to go without wasting time and getting you operational as soon as possible. We'll teach you how to not only set up the hardware so you can get analog reception, but also P25, DMR, NXDN, and trunking, all again with simple to use hardware and your existing computer setup. So for more information about this introduction to SDR training, please visit our website at scannerschool.com/courses.
Welcome to the Scanner School, a podcast dedicated to the scanner radio hobby. Class is about to begin. Here is your host, Phil Lichtenberger.
Welcome to Scanner School. My name is Phil Lichtenberger. My amateur radio call sign is W2LIE, and this podcast is here to teach you everything you need to know about the scanner radio hobby. This is session number 77. All the show notes and session materials can be found on our website at scannerschool.com/session 77. So today we're going to talk about some basic electrical terms. And again, I alluded to this 2 weeks ago in session number 75. We talked about troubleshooting your scanner radio. So I do apologize in advance for the way this podcast is going to sound. We had a family trip, a 3-day weekend, and it's now Sunday evening, a little after 10 p.m., and we got back today. I wrote the podcast up, and now I'm recording it. So this one, if it comes out sounding a little bit rushed, I apologize. I'm trying to get the basics down for you, and hopefully the long weekend didn't affect the podcast any. But yeah, long, crazy weekend, and here we are, last minute recording a podcast. So anyway, we're gonna cover some real basic electrical terms here, and again, I want to go through this because we talked about it again. Like I said 2 weeks ago, we talked about voltages and measuring with your volt ohm meter, and that's basically what you should have in your toolkit anyway. Is a very basic multimeter, something that does, that does resistance, something that does volts, either DC or AC, something that will measure current. And again, we're going to go through those basic terms here. And again, a lot of you guys who went through some sort of background with electrical are familiar with what we're going to talk about here today. But again, this is something for those who kind of have heard these things but are not really sure where this is going. Again, with Scanner School, I try to cover from the very beginning to the more advanced topics. I try and pepper them and alternate a little bit back and forth through them anyway, through the topics. So today is one of those more basic topics out there. And a lot of the way that we learn about electric is by comparing it to plumbing. And we compare this to plumbing because this is something that's tangible, something that we can relate to, something that we're all familiar with. Or we better be familiar with anyway. And that's the way that we, again, because we can't really see what's going on in an electrical system. I mean, a light bulb we can see, but what's going on in the wires, right? We can't really see the electrons moving, but we can see water flowing. We know what happens with water. So it's a good analogy, and we all kind of learn about electricity by going through the analogy of water. And that's exactly the way we're going to go through it today because, again, it's what kind of everybody knows. So let's think about it this way, right? We physically can see water. We have a basic idea what happens like when you kink a garden hose, right? You're adding resistance because you're restricting the flow of water, right? This is the kind of stuff we're going to talk about today. Again, if you have a garden hose versus a 5-inch fire hose, a much thicker pipe, more water flow can happen through that 5-inch hose than your 1/2-inch garden hose, right? So we're kind of familiar. We can visualize what we're going to happen here and what's going on. So not going to reinvent the wheel. This is the way I learned it. It's the way many people have learned electrical. If you go online, you look at Google, and you look at any electrical term, more or less, any website you go to is going to be referred to as water-based anyway. So let's go through a couple of quick things before we get started here. The basic one, the biggest or the most infamous or most famous one of them all is Ohm's Law. So one of the very first thing we learn about when it comes to electrical is Ohm's Law. Ohm's Law basically is the relationship between current and voltage and resistance. Okay, that's really what Ohm's Law is on a 30,000 foot view. So when you see Ohm's Law, it's basically written as I equals V over R. I is the current of the conductor in amps or amperes. V is the voltage across the conductor in volts, and R is the resistance of the conductor in ohms. So I equals V over R. Current equals voltage over resistance. Now, what I'll do is I'll put online, again, scannerschool.com/77, I'll put the Ohm's Law triangle. And what you can do with Ohm's Law triangle, which is really cool, is you can cover one of the values with your finger, and that'll tell you the mathematical formula to use. So again, if you were to cover I, you would get V over R. If you were to cover the V, you're looking for voltage, you get I times R. If you were to cover the R, you would get V over I. So you can kind of see how the formula really works. So again, it's very easy to calculate one unknown when you have two values. So let's take an example here. You know the voltage and resistance of a circuit. So you can easily figure out the current in amps that's needed through the circuit. Since volts over resistance equals current, then 100 volts and 10 ohms of resistance means you have 10 amps in this circuit. Likewise, 100 volts with 50 ohms resistance would be 2 amps. Said another way, if we know we have 50 ohms resistance and we have 2 amps of current, we must have 100 volts running through the circuit, or I times R. So again, I'll put this whole thing through there. It's very simple to figure out once you know ohms are and you've got the triangle. But I'll put the little triangle through on the website, scannerschool.com/session77. So again, we talked about Ohm's Law really quick just to get things going. So again, we just talked about Ohm's Law to get things going really quick. Volts, currents, and resistance. So what's a volt? Volt is basically one of the more common terms that you are going to hear. Example, your scanner runs on 12 volts. If you're in the US, your house is 120 volts. Overseas, 230 volts. Okay? But we all know there's a difference between a battery and your home electrical. We have DC, direct current, or AC, alternating current. DC can have a constant positive or negative charge. For example, your scanner requires 12 volts positive DC. Your car, 12 volts DC. Your computer power supply might put out positive 48 volts, negative 48 volts, positive 5 volts, negative 5 volts. Of course, you've got a ground, 0 volts. In AC, you have it's cyclic, right? It's a frequency. You have a positive and a negative. It's a sine wave. That's alternating current, positive, negative, positive, negative, positive, negative. And the frequency that happens here in the US is 60 hertz, or 60 times per second. You are going from through positive to negative and back to positive again. That's the cycle. Overseas, it's 50 hertz at 230 volts AC. So again, depends where you are, is the difference in not only the voltage, but also the frequency of that voltage. And what is the frequency? It's a sample or cyclic condition that happens over a certain period of time. We covered this, I believe, in session number 2 of Scanner School. So let's go back again. What exactly is a volt? A volt, again, going back to our water analogy, a volt is like your water pressure. It's how much difference you have in electrical potential. It's the electrical force, right? And if you want to get real technical with it, the scientific definition of this is 1 volt is equal to the current of 1 ampere to flow through a conductor having 1 ohm of resistance. So measuring volts is extremely easy. All you got to do is take your voltmeter and you put it across the item that you wish to measure the voltage across. So if you're looking to measure the voltage across your battery, you just touch the positive and negative terminals, and you'll see 12 volts. Hey, 9-volt battery, 9 volts. 6-volt battery, 6 volts. NiCad battery. Let's go back a couple weeks to the troubleshooting session where I was called out on this one. NiCad battery, 1.2 volts on a AA battery. I think I won't make that mistake again. Or 1.5 volts on a standard alkaline AA battery. All right, so now let's measure the current. So in our water analogy, the current is based on the diameter of our pipe. The thicker the pipe or the hose, the more water you could physically push through it. You could deliver a higher current. Example, your drinking straw can only deliver so much water. No matter how much pressure you put on one end of that water of that garden hose or your drinking straw, you're only be able to push so much water through it. Right? That push, that is the current. Okay. Again, water, the current flowing down a river. Right? We're all kind of familiar with this. Thicker wires, fatter pipes can handle higher current. Measuring current or measuring your amps. Okay, in order to measure your amps, you need to have a multimeter in line with the circuit. So unlike voltage where you can just run it in parallel, you actually have to run this in series. Your ammeter needs to be a part of the circuit. So you have to break the circuit and plug your ammeter in the middle of it. That's the proper way to measure this. Okay. Now, resistance is the opposition of flow of electrons. It's the exact opposite of how conductive something is, or how easily it allows things to move. So again, going back to our plumbing diagram, and here's a little story for you. If you live in a house with somebody that has long hair, you're familiar with this story. And again, I'm not alone with this one, but I tell you, my wife has a very bad habit of clogging the bathroom drain with her long hair. And it's to the point where I swear she must push this hair down the drain before she gets out of the shower because there's no trace of it when I get in, or very little trace of it. But after a couple, I don't know, maybe a month or two, I end up pulling Cousin It out of the drain. How do I know Cousin It is living in the drain? Because the water is really starting to slow up as it goes down the shower drain. And eventually, if I don't evict Cousin It, I end up turning my shower into a bathtub. Once you remove the giant hairball and you get rid of Cousin It, all of a sudden now the water flows right down the drain the way it's supposed to. I've gotten rid of all of the resistance. So just like taking a resistor out of a circuit and restricting the flow of electrons, Cousin It is gone, and I've shorted the circuit. There's no more resistance, and we measure resistance in ohms. So how do we measure resistance, though, with a multimeter? In order to measure resistance of a component, you have to remove it from the circuit entirely. And why do you need to remove the component from the circuit? So that you don't measure the entire resistance in the entire circuit when you're measuring resistance. But you don't have to do this to measure resistance, because if you know Ohm's law, you know the voltage, you know the current, and you can figure out the resistance. So you see how Ohm's law plays a key role in here? Now, again, theoretical values come into play here. But let's talk about a little funny story I have for you here too with this one besides Cousin It. When I was in college, I had an electrical class. I don't remember what electrical class this was, but I do remember the teacher was a real pain in the you-know-where. He would love to just watch you struggle, and he'd be like, oh, last year's class never had a problem with that. Or his favorite line was, I don't get it. 30 years ago, my students had an easier time going through this than you guys do now. You guys are nothing compared to my kids 30 years ago. And we'd be like, you know what? This really stinks. But we mustered through it, and we got through it. Maybe as he got older, his teaching style changed. Or maybe as his kids got younger, or we got stupider. I don't know. But whatever. It was college. The class was a pain in the neck. And, you're looking for something to get the stress out. And we had, I think it was 2 to 3 days a week, we had a lecture, and we had probably 2 days of lab or 1 day of lab. And it just took forever. It was a long class, and if you needed any help in his lab class, he wouldn't help you to about the last 10 minutes. So you had like 2 hours struggling through this thing, right? I mean, not to that. I mean, this is like, I don't know, a long time, a couple decades ago at this point. But I just remember this one because this was me just being a real wise ass in the middle of class. So we had to find out the voltage, right? And we had a variable power supply that ran in the entire lab class. So somebody would go in the back and they would set the variable voltage, and we'd all have to figure out, based on this unknown voltage, what would happen to the circuit, right? All theory, we'd run through all the math, then we would hook up all the components, then we would go through all the physical and see what the differences were, right? And see if we were in the standard deviation of, what the formulas came out to be. So we need to know what the voltage was, right? So, of course, what do? You stick your two prongs in the electrical outlet and say, okay, I have so many volts AC here. Well, the next question was, how many amps? So, of course, my group looks around and they say, well, how do you figure out the amps? And like a total idiot, I said, all in joking, all in good fun, I said to the person with the meter in the hand, just stick it in the electrical outlet and measure it out. Not thinking they would be like, okay, and they stick it in there. Well, guess what happens? Yeah, well, if you said things went pop with a loud bang and a huge flash, you'd be correct. We blew the breaker for the entire lab class. And I sat there dumbfounded thinking, I can't believe this person actually listened to me. And I looked around the lab class and I'm looking and going, everybody's station's dead. And I found the one person who looked just as dumbfounded as me. And I went, hey, you, what the heck did you do? To try and pull the blame to somebody else. And they're like, I didn't do anything. But in the damage was done. The teacher looked around going, who is the idiot that shorted out the system? Don't you guys know anything? So our lab group, yep. So anyway, the point here was you take one of those super, probably 20-pound resistors, AC resistors, and you measure the resistance across that, and you lock it into something real easy. You lock down that resistance, then you wire that in with your multimeter, right, in series back to the electrical panel or back to your outlet. You measure the current coming across it. Now you're not going to short circuit it out because you have the resistance in line. So now you've got your voltage, which we measured. We got our resistance, which we measured. And now we know the current going through it because, again, Ohm's Law states, right? So we know instead of plugging your meter directly into the system, directly in across the terminals to try and find out the current, because again, you got no resistance or next to no, you'll short circuit out, you'll trip your breaker. Again, Ohm's Law comes in and it saves your behind on that one. So again, pretty funny story from my my lab class, but again, I hope that teaches you a little bit easier than it taught my lab class how to do things the proper way. So again, that is volts, ohms, and resistance. So let's talk about impedance. All right, here's another funny story. We talk about impedance here. I had another electrical class, and we were talking about impedance. And there was a student in the class whose first language probably wasn't English, and he wasn't native to the U.S. And instead of saying impedance, he would say the impotence. The impotence. So as a 19-year-old or a 20-year-old kid, we all found it extremely hysterical that he would say, how do you figure out what the impedance is? And he would say it over and over again. So again, it was hysterical just hear him say, how do you solve for impedance? Anyway, impedance is, again, it's resistance. But again, I don't want to go too far down this rabbit hole here, because now you can quickly go crazy. And this is where electronic degrees come in, and this goes far and above where we need to go for our scanner radio discussion here. So we won't talk about right now, we won't go into the Q factor, we won't go into joules, we won't go into capacitance, reactance, or any other term that has to do with electrical that we're not worried about with scanning right now. I mean, we may talk about Q later on when we talk about antenna theory, because it does come into play a little bit there, right? But for right now, we're just going to curb the conversation when it comes to impedance. So when you have an AC circuit, you have voltage, right? You have frequency. You have your current. The electrical impedance is the measure of resistance when both the current and the voltage is applied. So it's a very simple form of impedance for the sake of scanning, and this is exactly what we're going to stop. It's just the resistance when you're talking about alternating current. Let's just leave it at that. And I bring up impedance because we're talking about resistance, but we are all familiar, we should be, with impedance when it comes to our coax, right? Our coax uses or is measured for 50 ohms of impedance. Our cable TV lines, 75 ohms of impedance. Ladder line, 300 ohms. Okay? It's not just you have a line and it's blank, right? Our antennas, our back of our radios, coax lines, they're all matched for 50 ohms of impedance. All right. Let's go on to one more. Watts. Watts is power. Watts is a unit of power. Watts is very easy to figure out. Watts is basically just voltage multiplied by current, or V times I. P equals IV, or P equals VI. Same thing, just depends on how you learn it. I always learned it as PIV. Let's go back to our basic plumbing system. So volts, again, is the movement of the electrons. It's potential, or the difference in the amount of pressure. In a water world, right, this is the pressure going through your pipes. Current, measured in amps, is the flow of water, the flow of electrons, right? What makes water flow? Maybe a pump. The pump creates the pressure. Resistance is the restriction of flow. It's the cousin it, the hairball, the wad, whatever it is that your kid flushed down the toilet. That's your resistance factor there. What are we doing with this water? What is the purpose of pushing this water down the pipe? Well, maybe in the old days, you used water to turn a wheel. Well, let's just say even now, you use water to turn a turbine to create electricity, right? This water turning a wheel is creating power in watts. Increase the pressure, you increase your wattage. Increase the current, you increase the watts. You increase the I or the V, you increase your power. So if you have, say, 110 volts with 5 amps, you have now power of 550 watts. So let's say you're trying to figure out how many watts you need in your circuit at home. Your house delivers 120 volts AC, right? That's what's in your circuit. Your appliance requires 600 watts to run. Well, how many amps? How much current do you need? P equals I times V. So you know P, power is 600 watts. V is 120 volts. You want to solve for I. Just like Ohm's Law, you have the triangle. So you have 600 divided by 120 equals 5 amps. Simple. So measuring watts is pretty easy. All you do is you hook up your watt meter in series with your transmitter. So if you're transmitting into a whole antenna system, do the world a favor. Unless you're testing out the antenna, transmit into a dummy load. You transmit a dummy load, your RF is absorbed, you're okay. The whole world doesn't need to hear you whistling, counting to 10. You shouldn't be doing that anyway. But again, that's how you test for watts. That's how you test for power. That's how you measure in watts. Sorry about that. So, again, watts is power. So now when we look on the FCC website, I'm going to throw a curveball in here. The FCC website lists a station's license in total output in watts, or ERP rather. This is the effective radiated power. The total radiated power that could be radiated basically from the station's antenna as compared to a half-wave dipole antenna. So, how do you measure ERP? And why do we even list these on the FCC website in ERP? Because if you had a license that said you can transmit for 50 watts and you throw a antenna on there with gain, well, guess what? You're not transmitting anymore at 50 watts. Because you have gain in that antenna, you are transmitting more than 50 watts. So this is how the FCC puts a cap on the entire transmitter from base station to the antenna. So if the FCC says that your ERP is 10 watts, that means that the effective radiated power coming outside on the main lobe of your antenna needs to be 10 watts or less. So again, why does the FCC do that? Let's just say, for an example, we have a 3 dB gain on our antenna. 3 dB gain will double the power or the loss, depending on how you look at it. Your 3 dB of attenuation lowers your receive by half. 3 dB of amplification doubles. Okay? So if we have a 10 watt transmitter and 3 dB of gain in our antenna, we're basically putting out now 20 watts of power, or just slightly less than 20 watts of power. Okay? So if we were licensed for 10 watts ERP and we set our transmitter for 10 watts, our antenna at 3 dB gain would effectively be radiating like it was 20 watts of power. That's why the FCC says 10 watts ERP. Okay, so let's change it up again. We can still have 20 watts ERP. But now we have a 6 dB gain antenna. That means instead of having 10 watts at the transmitter base station, we only need 2.5 watts of power coming out of that transmitter and into our 6 dB antenna to get our 20 watts. Well, how do you make sure you're within spec? You put your watt meter just before the antenna. If your watt meter just before the antenna measures 2.5 watts, then you know that your ERP, based on the math, would be under the FCC guidelines. So again, ERPs get a little bit more involved with that. When you want to measure ERP, you measure not only the transmitter, you can measure in any jumpers, you take for loss in jumpers, you take for loss in cavities, any type of combining you have in there. You add gain for any amplifiers you have in there. And at the very end, you have the antenna. So ERP is a very easy calculation. Now, again, from our point of view here as a scanner radio listener, we're not really too concerned about it. This is just something that you are aware of. All right, so before we wrap it up, I want to again thank our Patreon supporters. Now, again, Patreon is a monthly contribution to help keep Scanner School going. And I want to thank these following members for continued monthly support. Signals Everywhere, Glenn Bryden, Scott Vorder, Craig Harper, Dan, Jimmy Spelling, Ken Newberry, Kenneth Fowler, M.T. Bono, Mark Beebe, Raymond Hill, and William Arcan. If you would still like to help out Scanner School, but not on a month-to-month basis, we do have other ways that you can help support us. A one-time donation via PayPal, or if you're a big fan of Amazon like I am, you can come by our website, go to scannerschool.com/support, and by making an Amazon purchase, by using our link, you help support the podcast. If you're looking for a new radio, we have an affiliate set up with ScannerMaster. And if you're in the market for software, I highly recommend Butel Software. We are also an affiliate for Butel as well. So again, I want to thank all of you for your continued support. Thanks for listening. If I rambled a little bit too much, I do apologize for it. Like I said, we just got back today from a 3-day weekend. Spent the whole weekend in the sun walking through Sesame Place with my 5-year-old. And we had a blast, but I'm exhausted. And it's about 10:45 as I wrap this up on Sunday night. So with that, I want to say 73. We'll catch you all again next week. Again, this is Scanner School, a podcast where we teach you, hopefully, everything you need to know about the scanner radio hobby. 73.